Okay, so today I'm going to present you the additive manufacturing of Maraging steel. Why I've chosen Maraging steel? Because it's a special steel, and its names come from Martin's side and it's aging. That's why the name Maraging. Although most of the features of additive manufacturing are going to be similar or same, like of any other additive manufacturing of other alloys like aluminum, silicon, tin, magnesium, titanium alloys, but I've decided to use Maraging steel just to give an idea and to present some unique features of Maraging steel compared to other materials. So let's begin it. Okay. Okay. So Maraging steel. Maraging steel is basically a low carbon steel. Unlike the common steels where the carbon content is high, in Maraging steel we use very low carbon steel. And that as a result results in high strength to weight ratio, high corrosion resistance in the Maraging steel components, and high hardness, high weldability. So they are very useful. There are different types of Maraging steels available, like the one you can see on the screen. And here at Alutheme, we are mostly dealing with 300. And there are different alloying elements being used in Maraging steel to improve its mechanical properties, like nickel, titanium, aluminum, cobalt, and molybdenum. There are other elements which I have not mentioned because they are added in traces. Nickel, for example, it improves hardenability, cobalt, molybdenum, improving hardness as well, and wear resistance. And they are also stabilizing certain phases which are somehow not wanted or not required. And their applications are mostly in defense industries and in the production of hard tools. As you can see at the bottom of the screen, Maraging steel compared to 316L and titanium 6 aluminum 418 alloys, all of them are prepared using additive manufacturing process. There is a strong difference in their properties, in their hardness, ductility, and all that. So that's why Maraging steel are very commonly used these days. And however, compared to other materials where the other manufacturing variants have been used in the production of these alloys, Maraging steel is only being utilized using the laser powder based fabrication, specifically using the laser. Sorry. Let's go to the next slide. I know some of you are new to additive manufacturing and you might not have learned anything about selective laser melting process. So I want to give you a brief introduction. Selective laser melting process is an additive manufacturing process, but compared to other additive manufacturing process, it is a powder-based version where we use small powder particles to produce three-dimensional structures. What we do, like you have seen adding bricks to the wall, it is the same process, like you are adding material one by one to form three-dimensional structures. Here you use a very high-powered laser source to melt those powder particles to form solidified structures. It is having several advantages that you can make any kind of structure which you may not be able to achieve using conventional techniques. For example, auxetic metamaterials, they are having spatial mechanical properties that is unlike you have seen in the real world. And they can also produce some porous structures used in medical industries, like you can see on the right side. Some customized parts like lattice structures you can see on the top of the screen in the making of shoes. I think you can see the mouse hovering around those shoes. You can see these structures are now being easily built using additive manufacturing process. So there are several advantages of using selective laser melting process. Although the shoes I have shown you here is not a metal one, so that's not the correct example, but additive manufacturing is being used in the production of these components. So basically in the production of spatial structures, selective laser melting is definitely is having an upper hand. You can produce any customized parts. You can reduce lead time. You can uh, produce different kinds of materials as well. Compared to the conventional techniques, at present, selective laser melting is only able to produce or use some selective materials right now, not more than 50 or 60, I guess. But in the coming decades, I believe with the introduction of more materials, additive manufacturing is surely going to overpower or over means is going to take over the conventional techniques. More and more industries are joining, so it's hopeful. However, talking about the advantages, one cannot overlook the disadvantages. You can look at the support structures. and limited raw materials in the production of selective laser melting materials. This is one of a few of the disadvantages. And it's also not very useful in the production of in mass production, because in that case it will take a lot of lead time and high material costs is there. Apart from the mechanical perspective and the physical perspective, the selective laser melting process is having high surface roughness, poor ductility, and high residual stresses. And because of the non-linear microstructure, they are also having mechanical anisotropy in different planes. Now, what is selective laser melting process? Now, here you need recorder and powder delivery system, where you uh, insert the powder on the system and spread it onto the powder bed, and the laser is then used according to the CAD model. You can acquire it, means you can go use it from the computer CAD model, and you can use it to scan the specified regions to produce a three-dimensional structures, as you can see in here. The unique properties of selective laser melting process is that once you have powder particles being spread on the powder bed, the laser can scan these specified regions and melt them quickly to form a melt pool that looks like this yellow region. Can you see here the yellow one? Here you can see is representing schematically the laser is scanning the region. The center of this is going to be very hot, obviously, because it all contains melt pool, obviously, but at the center the temperature will be very high. And near the edges, temperature is going to be lower. As you can see in this diagram as well, the temperature at the center is very high, like 1869 Kelvin. And as you move away, the temperature is reducing. Why we need this melt pool to be, I want to talk a little bit more about melt pools. Melt pools, once they form, they start solidifying once the laser moves away, and it results in the formation of three-dimensional structures. Now, in order to produce three-dimensional structure, the most important thing is the overlapping of scan tracks or overlapping of layers. Why we do that is to just material consolidation. Otherwise, there will be lots of porosities between the scan tracks or lasers that will not be good for the final mechanical performance. Now, I will be talking about the heat dissipation rate more in the coming slides and reheating. So I've just mentioned that these are some of the processes that results in the uh, reformation of microstructure. For example, interim heat treatment. Let's talk about the reheating here. For example, look at this black screen here, black part. You can see the white lines, they are reducing here. That shows that if the new layers are being added, or the region, for example, let me explain you more clearly from here. If you look at this white one, if you are scanning this region, a melt pool will form here. And when the new layer is added, the melt pool will display it like that. I have shown them on the right side in order to make it more clear. So obviously the melt pool is, if the melt pool is forming here, it will still melt this blue region. But however, if you are scanning the fourth region, you can see this is not going to melt this blue region if it is right here. So that means this region after this fourth layer is going to still be heated, but not going to be melted because the melt pool is above it. So this is the reason that this region is going to experience a series of heating and cooling cycles that results in the development of microstructure and other phases. For example, the region which is very close to the substrate, the dissipation is going to be very high. Here, if this region is here, the dissipation is going to be very high. So it will experience a different set of heat treatment. But if the region is here, that is the heat dissipation is going to be very slow. As a result of which, this region can experience the interim heat treatment for a longer duration, and that can modify the grains and the precipitants nucleation. Apart from that, of course, there's one important aspect here that the interim heat treatments are going to be like for few microseconds, maybe like 10 or 20 microseconds in microsecond gas. So definitely the impact is not going to be that huge compared to the general heating treatment processes. But still, it can somehow modify the microstructure that we're going to see in the next slides during the discussion of mechanical properties. Now, this diagram can show you clearly that for a particular layer, for the blue region, for first few layers, the melting point, the region will be in the melting stage, that it will continue to melt again and again as the new layers are built on the top of it. But as far as the layers will continue to build up, new layers keeps on adding, this region will experience the maximum temperature, and this will keep on decreasing. And that can last for like maybe hours. So that interim heat treatment can significantly modify the microstructure of the additive components. Oh, so that's it for this slide. Let's go forward. One more thing, that this substrate is a platform bed, which is fixed on in the chamber on which these structures are built. So if there are overhang structures, if these structures containing overhang, the heat dissipation can be extremely poor. Now, how the solidification takes place in the additive components? You can see the formation of grains here. They are aligning in a particular directions. All of them are aligning towards the center. And you can see the other grains as well. This is the EBSD graph. What happens when the melt pool starts cooling? This region is having a zero solidification rate, although the gradient, the thermal gradient, is very high. So once it starts sliding, the grains, when the molten pool starts solidifying, the grains will nucleate here epitaxially, means from the same, directly from the bottom grains, following the footsteps. So they will orient randomly in different directions, but as we move forward, only those grains will grow up to the center, which are parallel to the maximum thermal gradient. And while subsiding the other grains, you can see some grains are pointing in the different directions, so they are subsided here. But those grains which last longer, they are in the maximum thermal gradient direction, maximum heat transfer direction, because here is where your laser direction is here. So this is the highest at the highest melting temperature, and this one is the cooling point. So obviously the direction is going to be in this. The maximum heat thermal gradient direction is going to be this one. Now what happens? These are the columnar grains, the long grains forms here. At the center of it, there are equiax structures, means circular ones. It is all because of the nucleation of grains due to undercooling and to achieve the lower state energy. That is the result that we get to see some fine structures, very small in size. You can also look into this graph. As the solidification rate or cooling rate is very high, like at the center, you can see this very fine structures, aqueous structures. I will show you in the next slide how they look like. And the columnar grains, they become quite large when you have the solidification rate smaller. For example, look at it here at this picture. At the center of the melt pool, you can see these are circular grains, or representing more like a hexagonal type, because in order to reduce the lower energy content. And the side grains, so you can see they are more like columnar grains. Similarly, here you can see some columnar grains here, and at the center you can see some cellular structures. This is the representation of the microstructure on the scan plane, means parallel to the scanning direction, and this is perpendicular to the scanning direction, or the build plane, vertical plane. Here you can see the grain structures are very fine, very small in size. On the contrary, on the build side, the grains are different and columnar and means stretched out. So this is the difference in the microstructure. This also translate into different mechanical properties, that is mechanical anisotropy in the structure, that we need to get rid of, otherwise if we want a uniform structure. Okay, the phase distribution. The unique property that is defining the Maraging steel is the phase formation. Now, looking at the XRD peaks, you can see that mostly two phases are shown here, martensite and austenite phase. Martensite having the preferred orientation around 110 direction, and the austenites are having 111 direction. Now, this is the as fabricated state we are talking about. There are different states like aged and solution treated, which we'll discuss later on. But right, the as fabricated state, you can see the martensite is the peak one, having a preferred orientation here, although it can also appear in different directions, but this is the most preferred direction. And there are some austenite formation here. Austenite formation is all because of interim heat treatment. As I said, the region, the blue region, experience interim heat treatment of cooling and heating sequences for hours. So that can result in the formation of retained austenite. And retained austenite is generally happening because of the elemental segregation. Now look at this diagram. Here we are having 18% nickel here, 18%. So during the cooling, when the cooling rate is very high, material starts segregating towards the grain boundaries. And what that happens that as a result of this, some phases can form, like austenite phases can form. For example, if the concentration of nickel or other alloying element increases, the austenite forming temperature can reduce from here to here. So you can see more austenite can form due to elemental segregation. That is why we see some austenite formation here. Contrary to this, in the conventional components, normally austenites are not seen. Or even if there are some austenites, the concentration are very low, is very low. So interim heat treatment regions near austenite forming temperature results in the formation of more austenite. And moreover, more intermetallics can form. Now, phase distribution. We can also talk about the major alloy intermetallic particles that precipitate in the Maraging steel. They are nickel 3, titanium, aluminum, molybdenum. They precipitate during the interim heat treatment. However, their sizes are very small, very difficult to detect using XRD. Mostly they are detectable using TAM or STM analysis. And during aging treatment, you can see they can grow in size, forming a bigger particles, and more nucleation can take place during the aging treatment. So why nickel 3 titanium is the most favorable one because of having strong affinity of titanium with nickel. So therefore, this particular intermetallic compound is the one mostly observed in the Maraging steel component, and that is also one of the major element in contributing the high strength in Maraging steel. Apart from that, there are other elements like nickel 3 aluminum, nickel 3 molybdenum. Nickel 3 aluminum is formed by replacing titanium, and nickel 3 molybdenum is formed because of better lattice fittings. And this is in metastable state. So you can transform into more stable one like iron to molybdenum during aging treatments. Like any other selective laser melted selective laser melted alloys, uh, Maraging steel is also having the similar characteristics with respect to the energy density and the applied laser power. You can see we need to optimize these energy densities and laser power scanning speed in order to attain the high densification. If we are not using the right laser power or energy density, then there will be a lot of pores, different types of pores, like keyhole types of gas-induced porosity can develop. Gas-induced porosities are generally formed due to the escape of the gases, and these pores are formed because of the incomplete melting of the fusion particles. Obviously, when you input less amount of energy, the particles will fail to melt. So high densification is a requirement here. Similarly, in the residual stress analysis, you can see that if the components are built near the substrate, near this platform bed, there's high heat dissipation. As a result of this, there is compressive stresses develop in the structure. But as we keep on adding more layers, the stresses transforms into tensile stresses, and this can result in the formation of crack during external loading, during fatigue testing. We can see these cracks can grow rapidly. So we need to minimize these tensile stresses from the surface in order to improve its strength. Talking about surface roughness, you can see the structures looks quite rough. Like here, you can see these, they look quite rough. You cannot use them in critical applications where high surface quality is required, because if they are being used in those conditions, they are definitely going to be fail quickly. So scanning direction, you can see their scan tracks are clearly visible. We don't need them, and you can see some balls type shapes here as well due to the balling formation because of the sparkling and the settling of those liquid molten pool on the surface. Similarly, on here you can see some unfused metal powders or some extra metal particles being attached to the surface. So most of these are because of this, because they are very fine in size, as a result of which uh, surface roughness increases. Moreover, the mechanical properties, you can see the as built is having a very high hardness compared to the conventional, which I have not shown here. The conventional can be having like 350 or 320 hardness. So these selective laser melted Maraging steel are having high hardness. If you heat them, their properties are going to differ. I will discuss a little bit of it in the next slides. Also, if you look at the as-built component, they are having high strength high strength, and the conventional components will be having some strength like that. Means the strength of conventional components produced using cast or wrought processes is lower than the as-built components. Now heat treatment. So if you look at this slide, you can see the hardness was quite high here, and this is the solutionizing temperature, which we generally do around 800 to 900 to 1000 degrees centigrade. And this aging treatments are generally done at 480, 500, 520 degrees centigrade. So when you do aging, the hardness you can see is rising significantly because of the precipitation of intermetallic compounds. That is the reason. So the typical SLM morphology remains the same. For example, the melt pool structures, the fish-like structures, and the braided-like structure on the scan plane will remain the same, even if you age it. But during solutionizing, they disappears completely because there the decrystallization takes place and the melt pool disappears completely. The grain size remains the same during aging because of the precipitation of the intermetallic compounds at the grain boundaries that pins them and prevent them from growing. As a result of which, new phases, also new grain boundaries can develop also between the new phases. As a result of which, low angle grain boundaries can increase. All of this can contribute to high corrosion resistance and poor wear resistance in some cases. But although the fine grains contributes to high wear resistance. So intermetallic density, of course, as I said, due to the interim heat treatment, the density is quite lower. They are very small in size and very fine precipitation can take place. However, during aging, these intermetallic compounds will increase in size and become bigger and are more contributing towards the strength. And that is why we saw the hardness rising significantly high. However, in the solutionizing temperature, that is heating at 800 to 900 degrees centigrade, they dissolves completely, reducing the strength considerably. So during the solutionizing, these strengths reduces. Why we do solutionizing is because we want to increase its ductility. As you can see, the ductility is rising significantly from the as-built conditions, and in the aging condition, the ductility is very bad. Also, residual stress is a major concern in the production of additive components. So there is a high tensile stresses here. During the aging, we can reduce some stresses considerably, but during the solutionizing stages, they can be eliminated out completely. So one can see the hardness here, 382 HV, here 540 HV, here the hardness can reach like 300. So there is a significant reduction here, but overall mechanical properties will definitely improve. You can see the strength is increasing during the aging, but the ductility is poor. And you need ductility to improve the overall strength. So what we generally do in the Maraging steel components, we solutionize them and then we re-age them. We age them again. As a result of which our properties can be improved significantly. For example, 1882, 1943, and the overall ductility will also improve. This one important paper I studied in the study of the Maraging steel using the selective laser melting process, in which some intercritical temperatures were used in order to produce more austenites. So you can see that during the as-built conditions, where the austenite concentration was very few, they started heating it during the solutionizing temperature, and then they later introduced some intercritical temperature within the austenite range. So austenite range is generally, you can see is here like 634 degrees centigrade to 796 degrees centigrade. If we heat our material between these temperatures, this can result in the formation of austenite phases. So more austenites can result. If you can look at here, the austenite concentration was increased from 4 to up to 64%. Although austenite, presence of austenite is negative to the hardness because it is reducing the hardness of the component. However, the overall bending stress was found improving because it improved the ductility. For example, if you look at this diagram, which we have already also shown before, these are different intercritical temperature treatment during the aging. You can see these are the austenite concentration on the graph. So as you are increasing the austenite concentration, there are different measuring techniques. One we have measured using EBSD, the other one was used using X-ray diffraction. So there can be different measurements because of different reasons there. I'm not going to do into details, but so you can see as the austenite concentration is increasing, the hardness is reducing. And here again, the austenite concentration decreased, the hardness also improved. Similarly here, overall bending stress, you can see in the intercritical range was found better compared to the as-built state. As-built state means the fabricated state. Similarly, here the aging temperature. So we can see that as we increase the aging temperature, the hardness is varying with respect to aging temperature. So we need to choose these temperatures very carefully in order to improve our overall mechanical strength and the hardness values. Now, as we have seen that we have discussed about the heat treatment process, there are some other processes like surface treatment. They can be mechanical based or the electroplating or general chemical based treatments also that can improve the surface quality of the system or the component. Why we do that? We do that in order to reduce the surface roughness, because you can see the surfaces are quite rough here, but when you see here, the surfaces are quite better. When you have correct surface, I mean having low surface roughness values, it can improve the overall mechanical properties like improving the fatigue resistance and also prevents stress corrosion cracking. Now, for example, this is a shot peening process. What we do, we apply some shots on the surface which plastically deform it and introduce some compressive stresses in the structure. Compressive stresses are good because they can prevent the growth of crack, and because during the tensile stresses they can grow and can result in early failure of the component. So these mechanical based surface treatment actually deform the surface plastically, introduce compressive zones, and introduce more dislocations in the structure that can walk in opposite direction to prevent the crack growth, and also somehow refine the grain structures. So it improve the mechanical properties overall, like improving stress corrosion performance, improving fatigue resistance, improving corrosion, and also wear resistance. Now, corrosion is one of the key chemical property of any element. We need to investigate it in order to make it last longer in the aggressive solutions. So the analysis of corrosion analysis was done on Maraging steel built by additive manufacturing process. Here, I have taken some of the studies on the conventional parts because not many studies are available on the selective laser melted Maraging steel components. You can see that aged samples are having the higher corrosion potential compared to the solution treated samples. Similarly, the aging, if you talk about the as built component, they will be here somehow. That is showing a much better corrosion characteristics. The main reason is because of the high porosity and high surface roughness that is, of course, present in all three of them. That is the reason we have seen that corrosion resistance was found relatively inferior to the rod samples. Although in some studies they have been shown similar, but most of the time they were shown slightly inferior because of high porosity and surface roughness. Why aged samples they are having lower corrosion potential compared to the as-built components, which I have not shown here? It is all because of the precipitation of intermetallic compounds. Now, as we know that there will be more intermetallic compounds on the surface, the characteristics of the oxidized oxides on the top of it is going to be different. So this discontinuity between the oxides can lead to different corrosion characteristics. Means weak structures, weak passive layers can be created. As a result of which, it will be easy for the aggressive solutions to peep in through it and destroy the surface. This another thing, like depending on the different chloride solution, it has been shown as you increase the chloride content, means making the solution more acidic, more aggressive, the corrosion potential definitely is reducing. The corrosion resistance is reducing. So, but these things I have seen that most of the metals they show the similar behavior. Means in the presence of high chloride content, or in the presence of different phases on the structure, the corrosion resistance reduces. So generally, we want our structure to be more uniform throughout. So next, and the final slide is about the wear resistance. We saw that if we heat the material and make the material more harder, it will be more difficult for uh, the balls or tungsten balls that we use for wearing applications to make the impression. So the structure becomes harder and the wear resistance improves if we make the material harder. So the compared to the as-built conditions, the wear resistance of the additively built Maraging steel component after heat treatment was found better, especially after aging, because of the precipitation of intermetallic particles like this one. And also because of the finer structures, you can see that compared to the solutionizing stage, it's much better. We have also carried out the finish machining treatment here. So that finish machining was done to improve the surface roughness, means reducing the surface roughness comparable to the rod specimens in order to improve the mechanical properties, especially of the surface layer. So we observed that using that, it significantly improved the wear resistance. However, compared to the heat treatment, the finish machining process was not that significant. So why we use Maraging steel is because it's very good and extensively used these days in the production of uh, hard tools, and and it also means being tested every now and then using additive manufacturing process. So that's the end of my presentation. I have included some of the slides for easy navigations. If you guys having any questions, I will be happy to answer. I know I have been very quick, so excuse me for this. It's very odd to present on the screen. This is my first time. I'm more used to present it on the in front of the people. So excuse me for that. Thank you very much.